Okay, so we've done lots of stuff with these perpendicular vectors. Today is the 25th of November. And, you know, where everything's got a right angle. And it's super easy because you've been using Pythagoras forever. You can use trig functions to find headings. You can use trig functions if you're given a resultant to find x and y components of the resultant. But what if, how do you find a resultant there? Well, I mean, graphically, sure, you could do it and there's your resultant. But that's not a right angle. And that's an intentionally extra difficult one. In reality, what we do is we break it down into x and y components. We add total x, total y, and then we go ahead and use Pythagoras anyway. So it's all about getting back to the triangles, finding triangles. Let's do, let's do the airline ones are always fun. So we have a plane that takes off, taxis down a runway for 900.0 meters, then takes off at an angle of 22.5 degrees above the horizon. After it has traveled for 900 meters, what is its resultant displacement? Well, as always, we're going to start with these kind of problems. I always start off by writing this. The resultant is equal to the square root of delta x total squared plus delta y total squared. Because that reminds me that that's what I have to get to. So that's where I start every single time. And then just to remind myself where those totals are going to come from, I'm going to write something like this. Delta x total equals delta x1 plus delta x2. Delta y total equals delta y1 plus delta y2. So I'm just laying out a logical path for myself to recognize what it is that I need. And in this one, I didn't color code my two displacements, but I've got two distinct displacements. I have D1, I have D2. So in D1, I'll do all this in purple. Delta x1 is equal to what? The whole darn thing? There's no y displacement. They're taxiing, aside from my bad drawing where it seems to y up a little bit, but it doesn't. That entire displacement, the whole 900.0 meters, is all on the x-axis. So, did I say y? Did I speak the words y? You don't know. You don't pay attention to what I say anyway. It's fine. Nobody does. Delta y1 is equal to what? 0. And we don't have cardinal directions here. We're not told if it's taxiing east or west. We're not given that information. We can say something like to the right. We can say forward. We can just call this a positive direction. It's Cartesian positive. So we can. This is a case where using the signs as a proxy for direction is probably our best bet. Well, in D2, is that displacement squarely on one axis or the other? No. But we have an angle. And so what we do is we divide this. And we now have delta x2. I'm going to move my D2 over here. Delta y2. All right. So what do we do here? Well, I'm going to go back to my green. Delta x2, the x is adjacent to that angle. So delta x2 is equal to d2 cosine theta. Now, I skipped a step there. So delta y2 is equal to what? You go ahead and jot it down, and we'll see if you're right. Good. So when we're doing longer, more complicated problems, I'll show you a few tricks for these because they will get longer and more complicated. At this point, guess what? Now, on regular paper, I would just actually use more paper. But here, and please, 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 use more paper here. Give yourself space. Give me space because I will give you partial credit if I can find your sub-values for things like d2 cosine theta and d2 sine theta. If I can find them and read them, and you reversed your trig functions, for instance, which happens fairly frequently, I'll give you partial credit for having gotten them or having, yeah, but I have to be able to see it. All right, so here, let's go ahead and get some values. Okay, so I've just put in my actual values. And do you get something like delta x2 is 831.49 blah, blah, blah meters? That's the thing that I usually do, is I put little arrows in next to my sub-values in these, because that's a good reminder for me. Now, in this case, everything on the x is pointing the same direction, and we only have one y displacement. So we don't have a whole lot of problems with sine. In the example problem that we're going to do together in a moment, we will have problems with sine. Let's get our delta y2 value. So I've got a raw value of 344.415, and it goes on and on and on. It's continuing. What I'm going to do next is I am going to draw what I like to call the big triangle. So I'm going to color code. There's my delta x1, my delta x2 is in green, my delta y2 is in blue, and I'm going to make my resultant, as is my habit, in red. Do you see the big triangle? Now, if I pull it away from all the other sort of junk, what I'm looking at is this. The reason that I very often pull away that large triangle is because you get so much other stuff on your first picture that it can be hard to see the overall image. And that allows me to understand where my angle is, where that resultant is actually in regards to heading. So I tend to set that aside for myself because it helps clarify. So now let's actually go back to where we started and get our delta x total, delta y total. Well, delta x total is easy. Delta x total equals 900.0 meters that away plus 0 meters. Oh, gosh, no. Delta x. Whoops. Plus 831.49 blah, blah, blah meters also that away. Okay, so I shrunk that and moved it over a little bit. What do I get? Notice that I am not rounding anything just yet. So I've got 1731.491 blah, blah, blah meters all that away. Now delta y total, that's the one that's easy because there is no delta y1. So delta y total equals 0 meters in any direction plus 344.41 blah, blah, blah meters up. These get really messy, they get really ugly, they get really chaotic, but it's okay. They're allowed to be. I'm going to set that there. I'm going to stick this up in the corner here so I can reference it when needed. Now I'm about ready to plug everything into the equation that's going to give me my resultant. Okay, this is just Pythagoras. You can do this in your sleep. So I'm going to square my two totals, add them together, take the square root, I get a resultant value of 1,765.413 blah 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 meters. Am I done? I'm missing one thing. And this is the other place where I think that drawing this really helps. How do I find that heading? Tangent. Yeah. Turn and face the strange tangent. Anything can be turned into a David Bowie song. So in this case, what's my opposite? So opposite equals delta y total. Adjacent equals delta x total. If you tend to screw up getting your heading, I would strongly recommend that you jot that down for yourself. It's helpful. So I'm going to go down here. Tangent of theta equals opposite over adjacent, delta y total over delta x total. Theta equals inverse tan function delta y total over delta x total. Go ahead and plug in numbers. So we all agree we have a theta of 11.25. In what direction? Straight up? I think you need to reference the horizon here. Above the horizon or above the horizontal. So we would write our final answer. How many sig figs do we have? 4?
3. The degrees.
Oh, the degrees, you're right. Good job. Okay, so 3 sig figs, 1765. So we would do 1,770 meters at 11.3 degrees above the horizon. Okay, not hard. Ready to do a more complicated one? Yeah, of course we are. We'll stop this and I'll make a separate recording.